Around 1815, in that era, uh, electricity was just beginning to be used. The battery had just recently been invented. And one of the leading scientists of the day was Sir Humphrey Davy. And he would give lectures on different aspects of chemistry and electricity. He showed how to get elements by running currents through different liquids and materials. And one of the uh, persons who got a ticket to see his presentations was one Michael Faraday. Now, Sir Humphrey Davy was injured in a chemical experiment, and so to get some help with his experiments, since he had damaged his eye, he brought in Michael Faraday. And around this time, they began to look at experiments that were done by other people. And there was one that was done in the Netherlands that said that the compass would point perpendicular to current flow. So up until this time, scientists thought that, well, if I have a current flowing through a wire, that the only force that was occurring was to push the electric field, or I mean the electric current through this wire. And so they thought that that was the only thing that would produce a force, some kind of electric force. That's where you get the term EMF, electromotive force. And they thought that was what was carrying this current through this wire. But they couldn't understand what was happening that would cause the compass to point perpendicular to the wire. And so in comes Faraday, and he kind of turns things on its head. And he says, well, what happens if we put a bunch of compass around a wire and make sure that all the compass north headings are facing the same way? Well, what do we see? And what he saw was this circular motion, or circular tangential flow around this wire. So what he thought and the way he pictured it was much like the wind blowing a flag. The electric or the magnetic field lines produced by the electric current were in swirls or circles, and the magnetic field of the compasses got interlocked in with this circular motion and would work like a flag in the wind. It would always blow in the same direction as the wind. So the compasses would orient themselves to match this circular flow. This was unknown. It was brand new in his day. So from his experiments we get one of the right-hand rules for current. This is just one. There's a couple that we're going to be dealing with this semester. But if we want to know what the magnetic field direction is around a wire, then all you have to do is put your fingers around the wire, point your thumb in the direction of the current, and the tips of your fingers tell the direction. So you notice how the hand is coming around from the bottom of the hand to the tips of the fingers. That tells us that the magnetic field is, in this case, is going in a counterclockwise direction. Now we can use the right-hand rule to look at a loop, current loop, and you notice that here the current is flowing in a counterclockwise direction. And if we use the right-hand rule, put our thumb in the direction of the current, our fingers are going to wrap this way so that our fingers go through the loop. And no matter where I go, point my thumb this way, my fingers are going to go through the loop. The magnetic field lines are always going to go in the same direction around this loop. Now, if we look at the shape of this, this just looks like the magnetic field due to a bar magnet. So we can thank Faraday for his experiments in defining how these magnetic fields are produced and the directions and how they relate to the electric currents that flow through wires.